Hello, AM here. I've been working on an experiment with one-dimensional four-cell or four-neighbor automations, and I've just made this tool that kind of explores the data I've gotten. So I'm making this video so I can demo it. So on the right, you have a visualization of the data set, and I'll explain what that is. And on the left, you have a window that just kind of gives the Python program a place to print out the automation. So it kind of does that in an ASCII style. And so on the right, there's four-cell automations. So the way you know how many automations you're going to get is sort of comes from how many possible inputs there are. So for Wolfram's elementary three-cell automations, there's 8 possible neighborhoods. So that means you have 2 to the 8 automations, and that was his famous 256 automations. With four-cell automations, there's 16 possible neighborhoods. So then that's 2 to the 16 different rules out there, and they happen to fit nicely in this 256 by 256 image. Up in the top left is the 0, 0 automation, or just in one dimension, the 0 automation. And down here is the 255 automation, or in one dimension, the 65,000 some automation. You can see the different pixels have different values. So what I actually did was I ran the experiment on a graphics card, and I ran every automation 100 times. And I was looking for something in particular. Let's see, I have some notes here. So to demo what I was looking for, I'm going to go into one of the areas where the image is 0 and show you what a consistent, basically it's a plot of varying versus consistent automations in a particular way of looking at that. So this is rule 28,793. Hit spacebar to run it. And you can see that this automation has sort of a coherent motion to the right. And basically the idea is every cell of the automation, you can sort of look at the previous iteration and see if the value you just wrote matches the neighbors to the right or to the left. So if the automation coherently moves over time, it will match more the neighbors on one side than the other. So you can sort of get a composite score of what direction the automation is moving. And this automation is very consistent. Another automation, and you can see that, I'm not sure if you can see on the video, but there's a score here that says direction minus 2,106. And all the runs are randomly initialized, so you won't get the exact same score each time. But the automations do have some signature. The rule has some influence on what the score is, even though there's a random initialization. So this one tends to go between about 2,800 and maybe 1,900. That minus. That's sort of how it seems to go. Another example would be, oh gosh, I messed up my note about where this one is. Found a good example for you guys. I guess this is as good as any. It's a little bit more wiggly, but you can still see that there's a coherent motion in the other direction. And this one's adding up to 5,680. So to sort of contrast, there's this one that goes in this direction. It has a negative score. And then this one, where'd it go? This one goes in the other direction and it has a positive score. And both these, this one's rule 1,771. Both these rules behave very consistently. But what I'm really graphing here is the variance. So if there's an automation that has a varying directionality, then to me that's an indication that it might be complex or it might be chaotic, or who knows? Yeah, who knows what's happening? But I thought it might make a cool pattern on this two-dimensional visualization. So we can look at one that has a high variance. Let's look at one over here. And this one looks like there's some sort of complex stuff, and these scores are pretty close to 0. Let's look at one. Let's try to find a cool one. Yeah, this is kind of interesting. So basically, I'm getting some indication that there might be something, sort of interesting happening here, because if we keep on running the automation, we can see that sometimes it's negative, sometimes it's positive. So that means that the way the automation's initialized actually has some effect on the overall direction. And this one's actually making kind of cool patterns. I kind of like this one. So what's the point in graphing all of them here? Well, I was sort of hoping that if you sort of had some way of representing all these automations in 2 dimensions, you'd be able to see some sort of patterns. And this is basically the simplest way you can possibly do that. It's just a rasterized array, meaning you start at 0 here, you go to 255 for the first row, and then you're back here at 256 in the second row, and you just go across, and you just read your array of all your results right into this image row by row. And there's some structure here, and I think it's largely because the dimension of this image, it's 256, which is a power of 2, and the rules operate in powers of 2. So it is logical to think that you're going to see some patterns, like maybe some vertical lines. I think this diagonal line's interesting. By the way, this diagonal line happens to be largely chaotic automations. So there's a few other points of interest too. So there's lots of little cross-hatchy things that show up. And I think it's kind of curious. If you look, there's sort of a rectangle here where you have lots of little cross-hatches sort of scattered around, little stitch patterns. And then there's another area down here that has more of them. And then there's a void without any, a void without any. And you have more little cross-hatchy stitches here, a void without any here, and then some more cross-hatchy stitches down here. And if you kind of take a step back, this is actually I just noticed this as I was making an earlier version of this video. In fact, like this is actually that same cross-stitchy pattern. So I suppose there's probably some bit that's 1 or 0 in all of these, and then flips. It might be interesting to graph, to take the way all these numbers were written into this image and graph which bits are what. But despite that, so it's still interesting that these little cross-stitchy things seem to be inside that larger pattern, but they're not really completely uniformly distributed. Like they're kind of evenly spaced, but not really. They're kind of going in squiggly lines a little bit. Like it's definitely a repeating kind of pattern here, but I don't know if they repeat in exactly the regular pattern. They seem to repeat in kind of a little bit of a random way. Another thing that's interesting is down here you have some regions where you have these like smeared out scores. And it's something about these triangle pyramid sort of automations that they seem to be like pretty robust to little changes. Because one thing to remember is that if I go up with the cursor, if I go up a row, so say for example from rule 52,604 to rule 52,860, that's actually a 1-bit difference in the rule, because 256 is it's a power of 2. So these two automations I think have a 1-bit difference in the rule. Likewise, if I go to the right or to the left. Oh, I suppose you could have an increment. You could increment 1, and a lot of bits would flip over. But in many cases, it's going to be just a 1-bit difference in the rule for these small motions in this image. And it seems to be, this pattern seems to be kind of resilient against small changes to the rule. And you can see different regions where it does that too. Like this region is very similar. And you can sort of see these smeared out parts. And they're all, as far as I've seen, like where you see like a steady gradient of scores, you're going to have a steady gradient of this sort of pyramid structure also. And then we've sort of left Triangle Town, and now we're it's a different kind of structure. So let's see, I've covered the stitches, I've covered the diagonal line, I got the little smeared out triangle things. There's some vertical lines there, but I won't cover those more. Yeah, so I think there might be other patterns here as well. Those are just the first things I've noticed. I'm gonna make this tool available. So if you have like some knowledge of Python, you can probably get it working. And that's yeah. So that's that. Thanks for watching.